Today is a really important day, as you might guess from the title, Fundamental Theorem of Calculus. And anytime you see Fundamental Theorem of, and then the subject that you are studying, well, you can guess it will be a big day. Now, Fundamental Theorem of Calculus has two parts, and I'll start with part one, even though, as we will see, part two is what we primarily use. Okay, so part one. Well, let me give you the setup here. Suppose we have some continuous function, and then I'm defining here, I'm calling this the integral function. It's capital I of x. What this is you integrate from this number a to x of f of t dt. Now this is something that we should use a picture to see. So I have a continuous function. I will draw a non-negative function just for visualization purposes. So we have some function here. Y is f of t. And then we have some a. And I'm going to draw it a second time, and we will see why in a moment. So redraw. I'm trying to draw the same function. Okay, so what is I of x? Well, we discussed this last time. It's the area from A to x, area underneath the curve. This area is this capital I of x, okay? Maybe I will put that here. This area is capital I of x. Now, let's consider the following. Let's consider I of x plus h. And just by me saying x plus h, you can maybe guess where we're going. Where have we seen, a f of x plus h and a f of x? Well, in the definition of derivative. So if that's x, let me move out a little bit, and here will be x plus h. And then this area here, we just move out by h, but this area is capital I of x plus h. Let me write that here. Okay, so far so good. Well, what happens when we take I of x plus h minus I of x? Well, if we think about this graphically, here was just translating from this picture, maybe x, right? And then, well, we know it's the area just of this little strip. And I can say more, that this is approximately, well, I can draw it here, right? It's approximately where this is x plus h, and then here we have height, f of x. Height is f of x. Okay, so this difference is approximately, well, this is a rectangle, supposed to be, and this is length h and height f of x. So you can kind of draw it here. It's approximately, here would be this rectangle, right? With height f of x, this x value, that would be the height, and then width h, and I have it schematically drawn over there. But now, what can I do? Just divide both sides by h. So we see I of x plus h minus I of x divided by h is approximately f of x. And this is this integrand evaluated at x. Now, I will just say, as h approaches 0, the approximation improves. What we get from this, well, if we take a limit as h approaches 0, it actually equals f of x. And the limit as h approaches 0 on the left-hand side is the derivative. So we get, and I'm going to restate this just in one moment, but we get that I prime of x is little f. Okay. Fundamental Theorem of Calculus, Part 1. Well, technically, it is on the board already. And let me just say, Fundamental Theorem of Calculus, people will write as FTC, just as an abbreviation. Okay, well, first of all, I of x, which we have discussed, this is a function of x. Okay, you can think area or signed area up to value x. Here, but I will write it this way. Now, I'm just going to recopy this. What does this say? It says the derivative of this function equals little f of x. And this is part 1, okay? Now, part 2, let's immediately move into part 2. Part 2 says if capital F of x is any antiderivative for little f of x, then if we integrate between a and b of f of x dx, we get capital F of b minus capital F of a. And this has other notation. It looks like this. You will see capital F of x evaluated between a and b. So this, I will just add here, this is sort of notation for exactly what is above. And we will see that as we work definite integrals. And I alluded to this last time when we were using geometry and area to calculate a definite integral. And I mentioned that we would learn a way to calculate them that is no more challenging than finding an antiderivative. And that is this. It's Fundamental Theorem of Calculus, Part 2. And this follows from Part 1. Maybe if you're interested in seeing how it follows from Part 1, stay until the very end of the video and I'll go over it then. But what we really want to do is be able to use this. So let's do an integral that we did last time using areas. Let's see, we went from minus 4 to 1 of 2x plus 4 dx. We had this last time, which was we calculated areas of triangles and used signed area. But you see, using Fundamental Theorem of Calculus, what's an antiderivative for this function? Well, this would be, we integrate 2x, we get x squared. And then we integrate 4, we get 4x. And then this is evaluated between minus 4 and 1, okay? So we evaluate, and I mentioned this terminology last time, little a is called the lower limit of integration. Little b is called the upper limit of integration. So we evaluate at the upper limit of integration, we get 1 plus 4, and then subtract off, evaluate at the lower limit of integration, minus 4 squared, oh, I need a parentheses, and then minus 16. But you see, this is 16 minus 16. This is 0, and so we just get 5. And this is what we calculated last time using triangles and signed area. Let's do another example. What if we wanted this? Let's go minus 3 to minus 1 of 1 over x dx. And this is maybe the first time we realize why, in fact, we do need absolute values for an antiderivative of 1 over x, because this certainly makes sense if you think geometrically, right? Oh, I'll use this beautiful pen. If I quickly, maybe down in this corner, graph 1 over x, it's more or less like this, and like this, okay? Basic shape. And then -1 to -3 would be out here, okay? It's just a sketch, it's not accurate, but we can certainly, this is an area and it's underneath the x-axis. This will be a negative value, but this is something, right? It would be negative the area of this blue region. Okay, but now we integrate. We get ln, absolute value of x, evaluated between -3 and -1. This is why we can't just say ln x, because we could not evaluate at the upper and lower limits of integration. Okay, but now let's continue. We get ln, absolute value of -1, minus ln, absolute value of -3. Well, here, this is just ln1, which is 0. So the answer is negative ln3. Okay? This is this definite integral. Our next two definite integrals, maybe I will start over here. The first thing I would do is I would rewrite this as a power. This is the -2/3 power. Okay, now we integrate. Find a capital F of t. Well, this would be, we have a 2, then we add a power, divide by the higher power. This would be 1/3 divided by 1/3, evaluated between 1 and 8. And here, this is 6, t to the 1/3, evaluated between 1 and 8. And now we just take 6 times, this is the cube root of 8, minus 6 times the cube root of 1. The cube root of 8 is 2, this is 12, minus 6, we get 6. Okay, now for this one, whenever I see 1 over 1 plus x squared, immediately I think of the tan inverse. This is the antiderivative here, or an antiderivative. So we get tan inverse of x evaluated between 0 and 1. This is tan inverse of 1 minus tan inverse of 0. Tan inverse of 1, we've evaluated this more than one time, I think. This is where the tangent is 1. Sine and cosine are equal, and the angle is between minus pi over 2 and pi over 2. This happens at pi over 4. And then here, this says the tangent is 0, or equivalently sine is 0, and you're between minus pi over 2 and pi over 2. That happens where the angle is 0, so we get pi over 4 here. Okay, so here are two definite integrals that we used the fundamental theorem of calculus for. Now we want the area under the curve of 5e to the x from x equals 0 to x equals ln 4. And just a comment, we note that 5e to the x is always positive, and so the area under the curve is the definite integral from 0 to ln 4 of 5e to the x dx. Now, unlike when we were using triangles and rectangles to calculate area, this one, it's a curve, right? It's not a geometric shape. And so the way to calculate this is really fundamental theorem of calculus. When we integrate 5e to the x, well, we get 5e to the x, and then this would be evaluated between 0 and ln 4. This is 5e to the ln 4 minus 5e to the 0. Now, e to the ln 4, this is 4, because e to the x and natural log x are inverse functions. So this first term is 5 times 4, which is 20, and e to the 0 is 1. We get 15 for this area. The next question, find the average value of the sine function on the interval 0 to pi over 2? Well, briefly at the end, I mentioned the formula for average value of a function. We take 1 over, if it goes from a to b, we take 1 over b minus a. This is the length of the interval. And then you integrate from a to b of the function dx. Okay, so this quantity is the average value that we are looking for. Okay, well, this is just here, this is 2 over pi times this integral 0 to pi over 2 of sine x dx. When we integrate sine, negative cosine. So this is 2 over pi times negative cosine x evaluated between 0 and pi over 2. Okay. The upper limit, cosine pi over 2, this is 0. So we get negative 0. And then subtract off, cosine of 0 is 1. So we have like this. Okay, so the average value is 2 over pi times 1, which is 2 over pi. This is the average value for sine x on this closed interval. Next example, well, it looks kind of similar to the last in that we see some trigonometry and we see 0 to pi over 2, but the function is different. Well, also we're not asking average value here. So here my integrand is sine to the 5th of x times cosine x dx. And how would we compute this definite integral? Well, let's back up for a moment and ask a slightly different question. How do we find this? Sine to the 5th of x cosine x dx. Because fundamental theorem of calculus is so wonderful, if we can compute an indefinite integral, then we can compute a definite integral with the same integrand. Well, here, if you look at this, this is substitution, right? So let's work through this, and then we'll use an antiderivative that we calculate and fundamental theorem of calculus to find this number, right? Every definite integral is a number. Okay, let's do this. So here, u is sine of x, du is cosine x dx, right? Why is u the sine of x? Well, it's really sine x to the 5th, and we have exactly the derivative of sine in our integrand. So I have, as I was just saying, I have exactly du. This becomes an integral, is u to the 5th du, and then we integrate with respect to u to the 6th over 6 plus c. Finally, we go back to x, and the last step is composition. We get sine x to the 6th power over 6 plus c. Now, given this indefinite integral, or this capital F of x plus c, we can then address this. Maybe I will do this one in brown. So we know this is sine x to the 6th power over 6 evaluated between 0 and pi over 2. Okay? And then this would be sine pi over 2 to the 6th power, or I could even write it like this, put the 6 here to match how the 5th power is in the integrand, and then minus evaluated at 0. Well, the sine of pi over 2 is 1, and the sine of 0 is 0. So this is 1 to the 6th over 6 minus 0, the answer is 1 over 6, okay? And how I did this was when I had a substitution, okay? I ignored my upper and lower limits of integration initially and just found an indefinite integral, and then I used that to finish the problem. So I had a capital F of x, evaluate at the upper limit, evaluate at the lower limit, take the difference, okay? Now, there is another way, which I personally prefer, to compute definite integrals using substitution. And so let's talk about this other way now. The idea behind this other way that I mentioned is, instead of first finding an indefinite integral, finding a capital F of x plus c, and then going back, evaluating at the upper limit, which is an x limit of integration, evaluating at the lower limit, which is also an x limit of integration, and taking the difference. This other idea is we convert the definite integral into a definite integral which is entirely of u. So let's write what that might look like. We start off with an integral, say a to b of f of, let's say g of x times g prime of x dx, okay? Then we convert through u is g of x. We would convert this to an integral of f of u, du. But you see, really, this is x limit of integration, x limit of integration. And so over here on the right-hand side, these need to be u limits of integration. So u, when x equals a, u would be g of a. And when x equals b, u would be g of b. And when you do this way, you never go back to x, the original variable, because this on the left-hand side, this is a number, okay? And bounds are x. Function is x. Differential is x. Okay, then we move over here to the right-hand side, and this is a number. Bounds are, we have u limits of integration. Function of u. Differential is u, and they're equal. And so this way I prefer, because I don't have to go back to x, and it's very fundamental to the notion of substitution, where every single thing in your integral gets changed to something of u, and in this case including the limits of integration. So let's go back and do what we just calculated, where I change my bounds. Then we will do some more examples. We just did the integral 0 to pi over 2 of sine to the 5th of x cosine x dx. Okay, well, it starts very similar. It starts, oops, sorry about that, as u is sine x, du is cosine x dx. We have exactly du in our integral. But then I need to change the lower limit and the upper limit to u limits, because just as it says above, this is from x equals 0 to x equals pi over 2, okay? So let's do that part now. When x equals 0, u is, well, this gives us the relationship right here. Okay, u is sine of 0, which is 0. When x equals pi over 2, u is here, sine of pi over 2, which is 1. Okay, so all of this I would put in a box, and now we convert this entire definite integral to a definite integral of u. Goes like this. It's an integral 0 to 1. We have u to the 5th du. This is, well, we integrate u to the 6th
over 6 evaluated between 0 and 1. We get 1/6 minus 0, which is 1 over 6. And it's the same value that we had before. Like I said, the nice thing about this is you notice I never went back to x. And this is a definite integral, and then I transformed it to another definite integral, but it's one of u. So I integrate with respect to u, evaluate the u limits of integration, take the difference, and then I have a number. Now, we'll do some more. I will just say I personally always change my limits of integration. For me, it's easier. But one thing I'll caution you that you do not want to do is you do not want to maybe not change the limits and write u to the 5th du and keep the 0 to pi over 2. Okay, I've seen that in students' work, and it's incorrect, because if you kept this 0 to pi over 2, you'd get pi over 2 to the 6th divided by 6. Well, that's definitely not the right answer here. And then similarly, if you do change to an entire integral of u and the bounds are u, you don't want to go back to x and then evaluate at u limits or something like this. So I would just recommend, if you want to, as we first did this problem, come to the side, calculate a indefinite integral, which gives us a capital F of x plus c, and that does go back to x, and then jump back into your definite integral of x, evaluate, take the difference. This is a fine way to do substitution using a definite integral. Or you can always do it this way, where you always change your bounds. So in the end, you're just calculating a definite integral of u, and you don't go back to x. Whichever way you choose, I would try to do it the same way every time so that you don't get confused and start mixing the two, because we never want to mix u's and x's or u's and t's or something like this. And that includes mixing x limits of integration when you have an integral with respect to u. It's too easy to make mistakes that way. Okay, so let's do some more examples now. Here are two definite integrals we will calculate using substitution. Here, up inside the exponent of e is 1 over x, and we do see a multiple of its derivative in the integrand. So u is 1 over x, du is negative 1 over x squared dx. We have handed to us in our integral 1 over x squared dx, which is negative 1 times du. Now these three lines I would write if it was an indefinite integral with substitution, but then I have this extra part of changing my bounds, because these are x bounds or x limits of integration. So when x is 1, u is 1 over 1. I use this here. Maybe I will add this. You use this relationship to figure out what u is, right? U is 1 over x, so u is 1 over 1, which is 1. And when x equals 2, u is 1 over 2, which is a half. Okay? So all of this is my work here that I put in a box. Now I can write this entire integral, which is an integral of x, as an integral, a definite integral, in fact, of u. So this would be, it's an integral, u goes from 1 to a half, and then we have e to the u, and then minus 1 du. Now I could, if you want to look at this integral with the lower number as the lower limit of integration, we discussed this last time, it would multiply this through by minus 1. So this is, I could just multiply this by minus 1, it turns to a plus 1. So this is the integral from 1/2 to 1 of e to the u du. And then I integrate with respect to u, like this, you notice I don't go back to x because this here or this here, either one, it's entirely of u, meaning these are u limits of integration, function of u, du, okay? So then I get e minus e to the 1/2, which is square root e. And this is my answer here for this definite integral. Now, let's move on to the one on the right-hand side of the board. And I will go through the same type of steps. I see t squared plus 3 underneath a radical. And so this will be my choice of u here. Then du is 2t dt. We have t dt. This is 1/2 du. Okay, so far so good. Well, and maybe I can put them over here. I will change my bounds to u bounds. So when x equals 1, u is, well, you look at this relationship. It's 1 squared plus 3, which is 4. And when x is 3, u is here. 3 squared plus 3. 3 squared plus 3 is 9 plus 3, which is 12. Okay? This is all of the work that I need. Now let's write this definite integral as one of u. So this is, it's an integral. U goes from 4 to 12. And then we really have u to the minus 1/2. And then we have times 1/2 du. Okay? Now, integrate with respect to u. Well, what do we see here? We see 1/2 u to the minus 1/2. That just shouts at me the derivative of square root, right? So here, if we integrate this, we get square root u evaluated between 4 and 12. And you could, if you wanted to add a power, divide by the higher power, you get the same thing, right? You'd have u to the 1/2 over 1/2, and then when you multiply by this 1/2, you just get u to the 1/2. Okay, so this is the square root of 12 minus the square root of 4. We get 2 square root 3 minus 2. And this would be our final answer. That would be the value of this definite integral. Here's one more definite integral using substitution. The integral from e to e cubed of ln t squared over t dt. Well, we see inside the parentheses natural log t, and the derivative of natural log t is 1 over t dt. So my u here is ln t. Maybe I'll do this here. U is ln t du 1 over t dt. And we have exactly du in our integral. But then we change our bounds. U is natural log of e, which is 1. And when t is e cubed, u is natural log of e cubed, which is 3. Okay, so this is all of my side work for this substitution problem. And then this integral is, it's the integral. We go from 1 to 3. And then we just have u squared du. This is u cubed over 3 evaluated between 1 and 3. We have 27 over 3 minus 1 over 3. The answer here is 26 over 3. Okay, this is the value of this definite integral. One more integral for today, and this is not substitution, but this, which we're integrating an absolute value, it's really going to lead us into the next lesson, which is area and the definite integral. But to integrate this function, we need to think about what is the absolute value of x minus 4. Well, it's piecewise defined, really. It's x minus 4 if x minus 4 is bigger than or equal to 0. And it's negative x minus 4, which is 4 minus x, if x minus 4 is less than 0. Now, I can just change this. This says x is bigger than or equal to 4, and this says x is less than 4, right? Just adding 4 to both sides of the inequality. Okay, so if we go to integrate this, the absolute value x minus 4, this is, first I will use a property of definite integrals that we discussed last time. This would be an integral from 0 to 4 of absolute value x minus 4 dx plus an integral of 4 to 5 absolute value x minus 4 dx. Right, this was the property from last time. Depending on whether x is bigger than 4 or less than 4, we have two different formulas for absolute value x minus 4. And so, let me put this in a box. We would then have integral 0 to 4. Well, when x is less than 4, this is absolute value x minus 4. And then when x is bigger than 4, so between 4 and 5, this is absolute value x minus 4. Okay? And now, oh, I didn't put my limits of integration. Sorry about that. But now this is what I want to calculate here. And this I can handle because it's a sum of two integrals. So we get 4x minus x squared over 2 evaluated between 0 and 4, and then x squared over 2 minus 4x evaluated between 4 and 5. Oh. This is 16 minus 8. Then when we evaluate at the lower limit of integration, we get 0, okay? And then plus, evaluate at 5, we get 25 over 2 minus 20. And then subtract off, evaluating at 4, we get 8 minus 16. This is 8 and 8. 16 minus 20 gives us negative 4, which is negative 8 over 2. And then we have this plus 25 over 2. This is 25 minus 8, or 17 over 2. Okay, so this here, 17 over 2, this is this definite integral. I am finished with my examples, but if you are interested, you can continue to watch to see why is it the case that part 2 of the fundamental theorem of calculus comes from part 1. Part 1, which is if we differentiate this with respect to x, we get little f of x. This we discussed, we looked at this I of x and area, right? And so this we sort of talked about why that was true, and then I just wrote this. And so assuming part 1, let's see how part 2 follows from that now. So we begin part 2, it says if capital F of x is any antiderivative, and then it says some things. Well, what you see from this relationship immediately is that, maybe I will underline like this, that this thing, this integral from a to x of f of t dt is an antiderivative of little f. That's exactly what this says. Okay, but now capital F here is another antiderivative for little f. And we know any two antiderivatives differ by a constant. And so I will just say, using part 1 of the fundamental theorem of calculus, we get that capital F of x will be this antiderivative plus c. Okay? These two, just like I said, will differ by a constant. Well, let's just evaluate both sides at x equals a. Both sides at x equals a. We get f of a is the integral from a to a of f of t dt plus c. Well, what is a definite integral where the lower and upper limits of integration are the same? It's 0. So this would be 0 plus c. And you see here that capital F of a is this constant c. So now if I rewrite this, I get that f of x is the integral from a to x of f of t dt plus capital F of a. Okay? Well, all that's left to do now is evaluate at b, but then subtract f of a from both sides. So I will just say in particular, for x equals b, we have, and then I get f of b minus f of a. Okay, so I evaluated at b and subtracted f of a from both sides, and this is an integral a to b of, well, okay, I'll leave it as t's here just to match. Okay, I could also write this as an integral of f of x dx is fine. But this is the fundamental theorem of calculus, part 2. And so you see it follows directly from part 1 and using some properties of antiderivatives that we have discussed already.